take on some other shape. So you want to make sure that you are staying in the range of x. This is called extrapolation. Or to extrapolate. Okay. Do not extrapolate, just predicting beyond the range of x. Not a good idea. You fit the model up to that particular point. We've already gone over this previously, but outliers are also something that you need to be aware of because outliers have a huge effect on the regression line. Every observation in regression is equally important, and so when you have an outlier, it's going to significantly change that regression line. So once again, positive data, positive trend, you fit a nice linear line to that data. What happens if you have an outlier? It is going to change the regression line drastically. Let's say one's down here. Huge outlier, you need to make sure you do the appropriate calculations. But now your regression line looks like this. Okay? Every single point is treated equally, given the same weight. So if you have these outliers, you want to make sure you remove those outliers and then proceed with your regression analysis. Okay, outliers are not what occurs on average, therefore they should always be removed when you find them. So 1, 2, 3 being the data is not normal. We talked a lot about the data for the errors. The errors are distributed normally. The mean for the errors is 0 with a constant variance for those errors. If we assume the errors are normally distributed, y is distributed normally as well. But if this assumption does not hold, the entire theory that we talked about, all of the analysis that we've done, does not hold either. So this has to be true. If your data is not normal, what you can do is a transformation. We're not going to go on to do any transformations. You do not need to do this on the project if you're attempting this problem. But you can transform x if it is non-normal. So you can look at the transformations. Maybe you will take the square root of x. You can take the natural log of x. You can take the exponent of x. 1 over x. 1 over square x, etc. So you might transform this so that it is normal, and then you can go on and complete all the theory that we've talked about. Not going to do this. Don't worry about that topic. You might do that in another statistical course later on. Those are your 3 main pitfalls for regression that you want to make sure that have not occurred before you go and do your analysis. One thing to know before we move on. So when you go on and you do some regression analysis, you will find that you often have statistically significant results. This is because the error is often very small in this case. But you have to remember that just because you have statistical significance, you want to think about the problem that you're talking about and make sure that it is practically significant to the problem. You're more likely to reject the null hypothesis in all of these cases, but you just want to be aware of the scenario that you're dealing with so that we have practical significance along with statistical significance. Okay? Some things to be aware of. Now what we'll do is move on to the final lecture. I just want to briefly go through the prediction intervals. Some of you have already seen this. I'm going to leave most of the examples for you to review later, but we'll definitely go through the prediction intervals so you understand where all of those calculations come from. And then I will show you the list of topics. Okay? So we have two types of prediction intervals that we can create for a particular observation that we're interested in. One of those is a prediction interval for the average. X star represents your value of X that you're interested in predicting. So we can predict the average of Y for a particular value of X. We're going to create a confidence interval for that because we want to see how much error we found in that prediction. What you're going to do is take Y hat to plus or minus your critical value based on the t-distribution, which is why I have it up over here. Multiply that by the standard error. We talked a little bit about the standard error computation last week. And then we're going to multiply that by number n. Take the difference between your value X star minus the mean squared over n minus 1 standard deviation squared. This is in the formula sheet or on the formula sheet. So you're creating an interval around the average value. That's some fixed target that you have. That is your confidence interval. We'll go through an example so we know how to substitute appropriately in for all of those values. The next one is to create an interval based on X star once again, but not for the average, for the actual predicted value. One above is for the average value of Y. Now we want to predict the exact value of Y, come up with a confidence interval for that particular value. This is for a brand new observation, and that is found again by taking Y hat. This is found by substituting into your regression equation, plus or minus the critical value times the standard error. And the standard error for this one changes slightly. It's going to be bigger than the one up here, because this is for the exact value of Y. It has a lot more variability in that than the true average. We're going to take 1 plus 1 over n plus the difference between this value minus the mean divided by n minus 1 times the standard deviation for the variance of X. Degrees of freedom again is n minus 2. Number of pairs minus 2. Okay, and this is designed to cover a moving target. Exact value of y is not necessarily a fixed target like the one above the mean. It's a moving target. This confidence interval is more narrow. This confidence interval is going to be wider because we're trying to cover an exact value. There's more error in trying to cover this exact value than to cover the actual average. The one above is always going to be more narrow. Wider because the standard error is often bigger. The closer you have your x star to the average, the less error you have in these intervals overall. Yes, sir?
Just to clarify, in the first one it's x star minus x bar, and the next one is x star minus x.
No, that should be an x bar, thank you. It's x bars. I think I said the mean, but I did not write it down. Thank you. Appreciate that. All right, so we're going to go ahead and look at that example here. The example here, I'm not going to go through the entire example. You all have that up there for you. We're talking about the lengths and the weights. Regression problem, you will see a regression problem on Wednesday. And one thing I'll tell you is that I will tell you which one is X and which one is Y. Usually that is a problem like part A of the problem, but I don't want people to start the wrong way and then continue on and have the wrong calculations, the wrong problem. So I'm just going to tell you, I will tell you X and Y so that all the calculations are going to be correct accordingly. I give you a table of values here. I'm just going to give you a few values because we're not going to go through the entire problem. The R correlation coefficient is 0.94. This measures the strength of the linear relationship between length and weight for the snake. This is very close to 1, meaning the majority of the points do fall nicely along the line. We have n equals 9 pairs here for the lengths and weights. And then we have the standard error calculation I've given to you is 1.64, how far each one of the data points differ from the regression line. I asked you in the beginning to identify the explanatory response, again giving that to you. The length is x, weight is y, so for some length of x we can predict the weight. And in the problem, I do ask you in part B to come up with the regression line. I'm going to assume that everyone can substitute into B0 and B1 and find the regression line. You should all be able to do this. When you do, you get 44.3 plus 0.123 times x. And again, I left out some information here. There's a chart with some means and standard deviations for x and y to come up with this regression line. Please make sure that you do use y hat. This represents the estimated regression line, not the true regression line. You should be able to interpret both the slope and the intercept for this problem. The length is given in centimeters, and the weight is given in grams. So we can say we want to interpret the slope here as the x as length increases by, what did I say next?
1 centimeter.
our weight is going to
increases
increase by 0.123 on average. 0.123 weights grams. Okay, so always you should be able to, of course, identify what the slope is, what it represents. For the intercept, what can you tell me about the intercept?
x equals 0.
Length is 0, and this is the intercept, but no practical meaning for the intercept because it won't make sense for length to be equal to 0. There's always no practical significance for intercept. Okay, good. From here, I do have you go on to create a 95% confidence interval for the slope, and then you interpret what that slope means, very similar to this right here, but you have two different values, a lower and an upper bound. The coefficient of determination for this problem will be found by doing what? R squared. What is R squared?
0.
88.36% of the variability in y, in weights, is explained by that linear relationship between x and y. Pretty close to 100%, or pretty high up there, almost 90%. So a good amount of variability in y is explained just by length, but there could be some other variable out there that's also helped to explain the length of snakes, just not the weight. Okay, now we're going to go on. A lot of this was review. We're going to go on and just talk about the prediction intervals really quickly. Calculate a couple of prediction intervals. I just want to substitute into the equation so you know how to use it, along with reviewing the t-chart once again. Okay, let's suppose that we have our value x star is 170 centimeters long, and we want to first predict the weight. If I predict the weight of a 170 centimeter long snake, I'm just going to substitute into my regression equation. So go ahead and do that. That is 44.3 plus 0.123 times 170. Substitute right in there. Again, all the calculations, make sure you complete these. And you get 65.21 grams. Okay. Good. Let's do the 90% confidence interval for the average snake with this particular weight. So we use this prediction. What should we expect to happen for the weight on average? Remember, this one will be narrower than the exact value. So we're going to substitute in here y hat plus or minus t alpha over 2, standard error, square root, over again. Yes. X star minus x bar squared, and minus 1. It's a little messy. So 90% confidence interval, T alpha over 2. If you want to draw the diagram, feel free. 90% is in the middle. That means you have 5% on each side. This is a T distribution with how many degrees of freedom? 7 degrees of freedom. T of 7 degrees of freedom. You can look here on the table and you can find it in this table. You can go to the bottom of the page. Here's 7 degrees of freedom. You have the upper tail probability. What is your critical value? So go ahead and substitute in there. You all have to answer. Well, I had it list down from before. What do I have? 65.21 plus or minus the 1.895. I gave you standard error in the beginning of the problem. The standard error is 1.64 times the square root of 1 over n, which is 1 over 9, plus our observed value 170 minus the average. I did give you the average beforehand as well. X bar is 152. Squared over root. This is 8 times. This is 35.338. Make sure that you can substitute in the appropriate numbers here. Yes, sir.
So is standard error SFX squared x bar, which we do in there? Did we ever have to calculate the SFX squared and the SFE, or is it always sitting in the tables?
I will give you all of the information that you need. I will give you the mean of the variance or standard deviation for x and y for sure. I think we did go over a computation for standard error, didn't we? So you might have to calculate standard error, but whatever is involved in those calculations will be provided to you in the problem.
Okay. And then for the standard error, that sigma of E of ij, is that going to be given to us?
Yes. Yeah, I'll give you everything for that computation that you need.
All right.
It would take too long to do any kind of these types of problems if I could give you so much information in class. So I just want to make sure you go over it so you know where all of the numbers came from. Again, please make sure you're going through these computations. It's one thing to sit up here and watch and to maybe just write this down, but when you're actually calculating it, you want to make sure that you can get the answers that we have. It's practice. The more practice you have, the more practice you get, the better you're going to do on the test. You will get 64.033 as your lower bound, 66.387 as your upper bound. This is about the average rounds based on this particular value that you're predicting. So you would say I'm 90% confident that the true average snake weight is between these two values for a snake that is 170 centimeters long. Shall I write that down?
And I can't quite tell when you're talking about standard error or when you're talking about standard deviation of residuals. When you say SE is bigger,
This is the variance of x.
but then we have SE next to T alpha. I thought that's standard deviation.
This is
Yeah.
the standard error that we calculated previously.
Yeah, I thought standard error was SE times the square root.
That is the entire standard error for the interval.
Yeah, but the SE, that's not standard deviation of the residual.
That's the standard deviation of the residuals. That's its own separate calculation. It's
Okay,
given
so
on the.
it's not standard error.
It's not standard. It's the standard deviation of the residuals. It's the standard deviation for every data point to the regression line. That's what SE represents. That times the square root is the entire standard error that we have for the confidence interval.
Okay.
Does that make sense?
Yeah.
Let me bring up I'll bring up the formula sheet as well. I'll write this one down for you. interpretation for this particular interval down at the bottom. Interpretation is very similar for the other interval that we're about to calculate. Any questions on this particular confidence interval? Nope. Do you feel comfortable creating the other confidence interval? Like to go through it? Okay, this is number, there's numbering of 1, 2, 3, 90% prediction interval. Okay, so this is just a prediction interval for 170 centimeters long. Looking at that exact value, not at the average. Interval is very similar to the other one, plus or minus the critical value times the standard error, again, the standard error for the regression line. Okay, this is the estimate of what we're estimating times the square root of 1 plus 1 over n. Difference between x star and x bar squared over standard deviation times minus 1. Okay, combining the standard error times the square root gives us the standard error for the regression or confidence interval itself. Substituting in here yields, this is 65.21 from the previous calculations, plus or minus 1.895 from our chart. Standard error 1.64 was given. Square root of all of this information. Just a lot of information here, a little bit tedious. When you come up with this, you get 68.533. This is, of course, in grams. Notice the interval is wider, again, because this value here is going to be wider in general. Trying to predict an exact value has much more error. So we are 90% confident that the prediction of a snake for 170 centimeters long is between these particular values. So this is the exact value. It's going to be somewhere between 61 and 68 versus the average values that we found before. Do you feel confident in creating some prediction intervals on Wednesday? 90%. I'll take that. 90% is pretty good. You said 20% out of the interval. That's pretty good. Okay, so let's go through everything that we've discussed in the last 3 weeks. It's been very quick. Couple of things to note over here. Homework score solutions will be posted. I have those all ready to post tomorrow. Your homework 4 is due tomorrow, so once I get all those collected, I will post those right away for you. Sample exam is posted. I recommend printing this out along with the formula sheet and working through that. How many people have done that? Just a few. Print it out, work through it. Don't worry about the time. Just try and work through it without any notes or anything. Post any questions on Piazza. Send me an email as well. Actually, all those get sent to my email anyways. Piazza is the best way to go. If you have, you can send me a private note if you want to send me a private note there as well. I'll have extended office hours tomorrow. Basically, all of class tomorrow will be one big office hour. So I'll come in. I'll try to bring any other information that might be helpful to you. Then I have office hours after class. I'll extend those another hour from 12 to 2 if you want to see me. So, we started off when I came back talking about ANOVA, analysis of variance. And this is where you're comparing more than two means to one another. You're going to look at the variability within the groups and compare that to the variability between the groups. So we talked about the model for that. We did actual hypothesis testing to determine if one of those was different from the others. We talked about the ANOVA table itself and how that's set up, the degrees of freedom, the mean squares, the F statistic, p-value, etc. We did all of that in R as well. And then we created Bonferroni confidence intervals if we did find statistical significance. So if we rejected H0 and found at least one of those is different from the other, we went on to create confidence intervals. I will give you the critical value for the Bonferroni confidence intervals if it's on the test. And then we went over all the assumptions for ANOVA and the notes. Moved on a little bit to categorical data. First started talking about estimating the proportion. We did that with the traditional method, just taking y over n, number of people with a characteristic over total number in the sample. We talked about the Wilson adjusted statistic. It's biased, but the standard error is lower than the traditional method. So we use that to create confidence intervals, and we did that using the Wilson adjusted as well. We then went on to talk about the goodness of fit. So we're looking at a hypothesized proportion, trying to determine if they're all equal to what we think that they're equal to. So we have maybe 3 categories, and we think the categories are equal to one another. So we'd say the category for A is equal to maybe 1/3, B is 1/3, C is 1/3. And then we go on to do a chi-squared test for this hypothesis test. If we have 2 categories, that's where we talked about doing those directional tests. So we can look at one being bigger than the other, vice versa. Using directional tests is where you have to look at the p-value. So if your calculations correspond with HA, you take half the p-value. If not, p-value is greater than 50%. And we went over assumptions for all of those as well. That was Chapter 9. Chapter 10 was more categorical data. This is where we got into talking about independence. Still, we're looking at those proportions based on the conditional probabilities. And doing the test of independence, you can either write out the statements for H0 and HA, or you can say the probability of A given B versus A given its complement. Did a test for a hypothesis test, again, chi-squared. And then we went into the confidence interval. Confidence interval was using that Wilson's adjusted once again, looking at the difference between those 2 proportions and interpreting what that meant in terms of dependence. We had some homework questions on that as well. After that, we started talking about risk. You should be able to calculate risk and relative risk. From both of those, you can calculate odds and odds ratios. Make sure you understand the interpretation of all of those. I put facts down because we talked about what happens when odds ratios are equal to 1, greater than 1, less than 1, and so on. We also created a confidence interval for the odds ratio, and that also told us something about the differences between the 2 groups. Last thing we talked about regression. We just finished that today. Again, I will give you explanatory versus response variables. I'll tell you what that is so you don't go on and do the wrong calculations. Know what the correlation coefficient is. That's R, little r. You know the facts about that. We did a hypothesis test for the correlation coefficient. Remember that being hypothesis is H naught rho is 0 versus HA. Rho is not equal to 0. So this is showing some linear relationship versus none. This is, I just want to make note of it, the same as saying beta 1 is 0, or beta 1 does not equal 0. So it's the same as testing the slope. If you happen to be doing that, our project question for regression, looking at the p-value for the slope based on the output for linear models is the same as looking at whether rho is 0. Okay? So that's how you can do the hypothesis test. Same difference. If you were to go in and do this in your calculator, you actually have those two options in your calculator. So feel free to write out your hypothesis test with the slope if you would like. Let's see. We talked about the true model. We talked about the estimated model. We just spoke a little bit about how to interpret slope and intercept today. Coefficient of determination, that's r squared. Make sure you know that those two things they mean the same thing. We did a confidence interval for the true slope. Confidence interval shows statistical significance if the interval does not equal 0 or does not contain 0. And then we just talked about two different types of prediction intervals based on a value of x. One being a prediction interval for the average value of y, the other one being a prediction interval for the exact value of y. And then we have interpreted both those intervals. Such fast? Slow. That's right. All right, so I will post this up for you. This is everything that we've gone over. I am still creating the test right now, so we're on Tuesday. I hope that's best day. Tuesday, when we come in tomorrow, you're going to submit your homework. I will knock out some of the lists that happen to not be on there, so you can narrow your focus a little bit more. Okay? This is basically everything we've covered thus far. And that is all the material I have for you. Okay? So, it's 10:45, 10:46. I'm going to be here for another hour. Please come and ask me questions. I also have office questions as well. So, I'll see you tomorrow.